Hey guys, we are Team Mercedes, and today we are going to talk about B-spline curves and surfaces. So here is a list of all our team members and the topics that each of them would be talking about. I am Divyanshu Gupta. So let's start. So let's dig into the technical details. So before we learn about B-spline curves, you need to know a major disadvantage of Bezier curve. In Bezier curves, to have a complex curve, we need to have larger number of control points, and as the number of control points increases, the degree of the curve also increases, and as the degree of the curve increases, we need to do higher computations to get the result, and this issue is addressed in B-spline curves. B-spline curves, which is short for basis spline curves, is a linear combination of n plus 1 control points and B-spline basis function, which is given by this formula: C of u equals to summation I equals to 0 to n, nip of u, pi, and u lies between a and b, and we assume that a equals to 0 and b equals to 1. In this formula, pi is a set of control points and nip is the basis function. The basis function nip of u is defined on a non-uniform knot vectors u, where the size of u is given by m plus 1 and m is equals to p plus n plus 1, where p is the degree of the curve or the order of the curve. Another thing that you need to know about B-spline curves, that it is a combination of multiple different curves. You can call them as segments, and this number of segments in a B-spline curve is given by n minus p plus u. So if you look at this image where P0, P1 up to P6 are the set of control points, X0, X1, X2, X3 are the knots. So n is equals to 6 and the order of the curve is 3, so the number of segments comes out to be 5. In B-spline curves, the knot vector determines where in the parameter range the polynomials start and stop as the curve is drawn. They are called knots because these values tie together the polynomials. And the basis functions are the basic functional building blocks that can be stacked on top of one another so as to have the features that we need. For B-spline curves, basis function is defined as an I, 0 of u is equals to 1, where u lies between ui and ui plus 1, 0 otherwise. For the rest of the values, ni, p of u is calculated using this formula. The basis functions can be written as a triangular scheme, where n0, p of u is the combination of two other values, n0, p minus 1 of u and n1, p minus 1 of u, and similarly the rest of the previous values are calculated. Now let's look at the curve point evaluation algorithm. This algorithm basically has 3 steps: find the knot span, compute basis function, and multiply with the control points. So if you look at the pseudocode, we first find the span, we compute the basis function, we initialize a variable c with 0, and then we multiply the basis function and the control points and add it to the variable c, and we keep on doing this till the loop runs out. So now let's look at the affine invariance property of the B-spline basis functions. Affine invariance means that when a list of data points is transformed under an affine transformation, the interpolating curve is transformed into in a similar fashion. In case of B-spline curves, an affine transformation is applied to the curve by applying it to the control points. Affine transformations include translations, rotations, scaling, and shears. So let R be a point in a three-dimensional Euclidean space. An affine transformation is denoted by phi, where the three-dimensional Euclidean space maps into itself and has the form phi of R equals to AR plus V. where A is a 3 by 3 matrix and V is a vector. The affine invariance property of B-spline curves follows the partition of unity property of the basis function. The transformation can be applied to the control points, which is quite easy, and once the transformed control points are obtained, the transformed B-spline curve is the one defined by these new points. Therefore, we do not have to transform the whole curve. So, let R equals to summation of alpha I pi, where pi belongs to the three-dimensional Euclidean space and summation of alpha equals to 1. Now we substitute these values into the equation that we looked into in the previous slide, which is this one, and we get this, where phi of R equals to summation of alpha I phi of pi. Now let's look at an example of affine invariance. On the left side, you see an image in a two-dimensional space, and on the right side, you can see that the image is projected onto an affine space and the transformations are performed in it. Now let's talk about strong convex hull property. The curve is contained in the convex hull of its control point. If u belongs to ui, ui plus 1 and I is between p and m minus p minus 1, then C of u is in the convex hull of the control points pi minus p to pi. So if you look at the image, the p0, p1, p2 and p3 is the convex hull, and the curve contained inside this hull is the B-spline curve. Another way of saying this is for a B-spline curve of order p, a point on the curve lies within the convex hull of p neighboring control points. So if you look at this image, the convex hull is defined by p1, p2 and p3, and the dashed curve is the B-spline curve which is contained inside this convex hull. For this, u lies between u3 and u4. If you look at this image on the right, the convex hull for this is defined by P1, P2, P4 and P3, and the dashed curve inside this hull is the B-spline curve. Now let's talk about the local scheme property of B-spline curve. A single span of B-spline curve is controlled by k control points. Therefore, changing the position of control point pi only affects the curve p of u in the interval ui plus p plus 1. If u is not in the interval, nip of u has no effect in computing p of u. And if u is in the interval and ni, p of u is non-zero, and if pi changes its position, ni, p of u into pi is changed, and consequently p of u is changed. So if you now look at this image. Originally, the curve was defined using the control points P0, P1, P2, P3, P4, P5, P6. And if you move P4 to P4 dash, the curve changes. Remember, when you move a control point, the segment that belongs to that control point is changed. The rest of the curve remains the same. Piecewise polynomials. A piecewise polynomial function is a function that is a polynomial on each of its subdomain, and the difference between Bezier curve and B-spline curves. Both B-spline curve and Bezier curves are defined by C of t is equals to x of t, y of t. For Bezier curves, x of t and y of t each are real valued polynomials of some degree d greater than 0, and for B-spline curves, x of t and y of t are real valued piecewise polynomials of some degree d greater than 0. For Bezier curves, x of t and y of t are each represented as linear combination of Bernstein polynomials of degree d, and for B-spline curves, x of t and y of t are each represented as linear combination of B-spline basis function of degree d. For Bezier curves, x of t is equals to sum of xi times bi of t, and y of t is equals to sum of yi times bi of t, where bi of t are Bernstein polynomials and xi and y are real numbers. Whereas for B-spline curves, x of t is equals to sum of xi times bi of t and y of t is equals to sum of yi times bi of t, where bi of t are B-spline basis functions and xi and yi are real numbers. So Bezier curves are technically also spline curves in which the curve has only one polynomial in the piecewise polynomial representing x of t and y of t. Piecewise linear approximation. The control polygon represents a piecewise linear approximation to the curve. As a general rule, the lower the degree, the closer a B-spline curve follows its control polygon. The lower the degree, the fewer the control points that are contributing to the computation of C of U0 for any given U0. If you look at the image, the control points are P0, P1, P2, P3, P4 and P5, and there are multiple curves. So a curve with degree P would be away from its control points, which is this one with degree 5. And the curve with degree 1 is the control polygon itself.
We are going to discuss about various continuities. The basic definition of continuity is where two curves are joined. There are two different types of continuities. One is geometric continuity and the other is parametric continuity. Parametric continuity means smoothness both of the curve and of its parameterization. That is, if a curve f is parametrically smooth, we can make a movie in which a car's position at a time t is f of t, and the motion of the car in that movie will look smooth. Coming to different types of continuities, C0, C1 and C2. C0 means the curve are at the same point where they join. C1 is they share the same parametric derivatives where they join. C2 also share the same parametric second derivatives where they join. Coming to geometric continuity, it means simply the smoothness of the track that the car leaves in the snow after it passes by. The three types of geometric continuity are G0, G1 and G2. G0 is the curve touches at the join point. G1 is the curves also share a common tangent direction at join. G2 is the curve also share a common center of curvature at join point. To make a note, parametric continuity is more expensive to arrange in the sense that it uses up more degrees of freedom, but mathematically it's simpler to deal with. In the following example, we are going to discuss about a quadratic curve on parametric values of u as given with a cusp at u equal to 4/5. A cusp is a point of transition between two different states or a pointed end where two curves meet. In the following example, we use both C0 and C2 continuities. Coming to the next example, this is also a quadratic curve and the first where the first derivative is continuous at u equal to 4/5. This example also uses C0 and C2 continuities here. The following example shows a quadratic curve on u equal to the following parameters. Here, the interesting point here to make a note is here it's P2 equal to P3. It means there is a double control point. Coming to the mathematical derivatives of a curve, the curve derivative formula goes like d by du of ni p of u. It gives n prime I p of u. We split the function. We get the derivative of the c of u function, which is c prime of u, which is finally the equation we get summation of I equal to 0 to n minus 1 ni plus 1 p minus 1 of u q of I, where q of I is p by u I plus p plus 1 minus ui plus 1 of pi plus 1 minus pi. We plug in the qi value in the first function, we get p summation of I equal to 0 to n minus 1 ni plus 1 p minus 1 of u pi plus 1 by ui plus p plus 1 minus ui plus 1. The pseudo code algorithm for it goes as follows. Here n is the number of control points, that is n plus 1. P is the degree of the curve, u are the knots, capital P corresponds to control points. The output of the array is ck, where ck of k is the kth derivative. Coming to the pseudo algorithm, we give the inputs as n, p, u, p and d. The output is ck, an array. We find the minimum of d comma p, where d is the inputs we give. We open a for loop and initialize ck of k equal to 0. Find two functions, find span and basis function. Further open a for loop, and then we get the final equation or derivative, ck of k equal to ck of k plus the basis function times p span minus p plus g. The curve derivative formula for ck of u, where it's the c of u function to the derivative of k, is given by summation of I equal to 0 n to the power of k ip of u pi. The parameters values of u goes between 0 and 1. Initially we take it as p plus 1, so we get the c prime of u as summation of I equal to 0 to n prime I p of u pi, where qi is the function we already discussed before, p by ui plus p plus 1 minus ui plus 1 of p I plus 1 minus pi. U prime is the functions between 0 and 1 with the value of p. We get the final equation as summation of I equal to 0 to n minus 1 ni plus 1 p minus 1 of u qi. In the following, left is a B-spline curve of degree 5. Its derivative, which is also a B-spline curve of degree p minus 1, defined by the n new control points. As in the Bezier curve case, this is a hodograph of the original curve. A hodograph is a vectorial visual representation of a solid figure. Here we can see that the hodograph in the first figure is with the control points and the second one is without the control points. Derivative curve degree 2. Let c of u be a summation from I equal to 0 to 4 ni comma 2 of u pi. It's a quadratic curve defined on parametric values of u as follows. To find that, we find the derivative of u prime and c prime of u, which is summation of I equal to 0 to 3 ni comma 1 of u qi. To find the values of qi, we start from q0 to q3, where qi values range between p1 and p0, q1 values range between p2 and p1, q2 between p3 and p2, q3 between p4 and p3. We can see in the following figure on the right. In a similar fashion, we also do it for a degree 3 or a cubic circle defined. For c of u is summation of I equal to 0 to 4 and I comma 3 of u p of I, where the parameter values of u are as follows. Even in this case, we find u prime and c prime of u, which is summation of I equal to 0 to 5 and I comma 2 of u qi. Even here we find the q values range between q0 to q phi, we get the following curve in the right. Here is an example of a quadratic, and it's a simple example of a quadratic and cubic curve, how it shows. Coming to higher derivatives, uh, as we know that the first derivative of a B-spline curve is also another B-spline curve, recursively applying this one, we can compute higher derivatives with no difficulty. On comparing second derivative, third derivative, and the higher derivatives are easy to compute. They are basically easy to compute with no difficulty. Coming to derivatives with respect to a knot. Here, the basis function derivatives with respect to a knot are found using divided differentiation and knot differentiation. Here, C of u is summation of I equal to 0 to n, ni of u, p of I. That uk be the knot multiplicity, d by duk nip of u. We for the following, if we take a curve, we get the right derivative of the following function, which is limit du tends to 0 nip u uk plus du minus nip u uk plus du over du. With derivatives with respect to a knot, we get the following function where the I values range between, if it ranges between 0 to k minus p minus 2, the value is 0. If it ranges between I equal to k minus p minus 1, we get the following expression. If it is I equal to k minus p to k minus 1, we get the following function. If I equal to k, and if I equal to k plus 1 to n, we get the following functions. The derivative of the left side is closely similar to the right side, as we can see here. To make them simpler, these are this is the left derivative and this is the right derivative. And the following figure in the below shows that it's a derivative function when it is when it is u10.
Hi, this is Raisha and we'll talk about B-spline surface. A B-spline curve can be extended to two dimensions to create a B-spline surface. A B-spline surface is obtained by taking a bidirectional net of control points, two knot vectors, and the product of the univariate B-spline function. As you see, this is the function for a B-spline surface where P of ij is the control points. Next, we will discuss about the steps to compute a B-spline surface. There are 5 steps to compute a B-spline surfaces. First is to find the knot vectors, knot span on the u direction, which is ui to ui plus 1. Find the knot vector on v directions, which is vj and vj plus 1. Compute the non-zero basis function of ni to pp of u, and compute the non-zero basis function of nj to q and qv. And then multiply the non-zero basis functions with the corresponding control points. Below is the extract where we show a B-spline surface of having u and v span as given below. Next, we show a matrix representation of a B-spline surface, where the degrees of P and Q are equal and they are 0, and NIP and NJQ are tensor product of the basis function. We apply U and V vectors as 1 by 5 and 3 by 5 to compute the value of S, which is a B-spline surface function. For efficiency, it uses local array to store the vector products of NJQ with PIK and then uses the product for further vector multiplication with NIP. Next, we talk about few of the properties of bivariate basis function. A bivariate basis functions are generally the function that depend on two variables. The first property is that of non-negativity. The basis function are non-zero for all values of NIP and NJQ for all values of I, J, P, Q, U, and V. Then we have the property of partition of unity. As we see, this diagram shows us the partition of unity function, where we see is that n of 4 by 3 of u and n 4 of 2 of v is outside that of the rectangle. The next property that we have are the local support, which explains that Ni of Pu and Njq of V, which are the two basis function, is always non-zero for Ui and Ui plus P plus 1 to Vj plus P plus 1. Next, we have the definitions of the other bivariate basis function. Differentiability. The continuity differentiability of the B-spline surface follows that of the basis function. Particularly, SUV is P minus K times of Q minus K, differentiable in the UV direction and in the UV and UV naught of multiplicity K. The maximal value is if P is greater than Q and Q is greater than 0, then Ni P of U and Nj Q of V gets exactly one maximal value. Next, we talk about the B-spline surface properties, which first of being the generalization of Bezier. Beziers are the fundamental importance in case of computer-aided geometric design. It is generally used as a base starting points of all kind of generalization. And then we have the endpoint of interpolation, where we interpolate the four corners of the curve, which is S0, 0, S1, 0, S0, 1, and S1, 1. The properties also follows the partition of unity function that we explained before. The next slide has the most important property of B-spline surfaces, which is the affine invariance. Basically, linear interpolation is affinely invariant. The affine invariance property also holds for B-spline curves. If an affine transformation is applied to B-spline surface, the result can be constructed from the affine images of its control points. This is a nice property. When we want to apply a geometric or even affine transformation to a B-spline curve, this property states that we can apply the transformation to control points, which is quite easy, and once the transformed control points are obtained, the transformed B-spline curve is the one defined by the new points. Therefore, we do not have to transform the curve. The next property that we have is the strong hull property. This property states that if u, v belongs within these cardinals, then SU of v is in the convex hull of the control points P of ij, where I0 to P is less than equal to I, and which is less than equals to I0, and J of 0 to Q is less than equals to J, which is less than equals to J0. The given figure is that of a convex hull property where the curve stays within the convex hull of the control polygon. Next, we have a property of B-spline surfaces, which is the control net forms an approximation using different degrees. As you can see in the figure, we have a little bit change in P and Q. A little bit change in the value of P and Q in respect of having the same control points has a degree of effect on the surface. The other important property is the local modification scheme. As we can see in the diagram, the scheme states that if Pij is moved, then it affects the surface only in the rectangle Ui and Ui plus P plus 1 and Vj plus Q plus 1. As you can see in the second diagram, we just move the point P3, 5 and it changes the rectangle 1/4 of 1 and 2/5 of 1. Next, we'll talk about the isoparametric curves. A parametric surface patch can be considered as a union of infinite number of curves. There are many ways to form this union of curves, but the simplest one is so-called the isoparametric curve. Given a parametric curve f of u, v, if u is fixed to a value, say 0.1, and let v vary, this generates a curve on the surface whose u coordinate is constant. These curves are very much in use in modeling libraries. As you can see, the given equation is that of a isoparametric curve. Here, we show an example of parametric curve by changing the values of u and v while making the other one fixed. This curve sweep out the surface if we let u change from 0 to 1 continuously. Similarly, the isoparametric curves generated by varying v covers the surface. Following figure shows a few of the isoparametric curves. When u is fixed, then we vary v from 0 to 0.8 and it generates a few types of isoparametric curve. Same way, when v is fixed and u is varied from 0.1 to 0.75, there are a few numbers of isoparametric curves that are generated. Then we show the surfaces with plane discontinuities. As we can see, there are two of the curves, two of the B-spline surfaces. One is a quadratic cubic surface with crease value given of u span and v span as follows, and figure 2 shows that of a bicubic surface with crease value of u and v being shown as below. Next, we talk a bit about the B-spline surface derivatives. Let u comma v is fixed, and generally one is interested in computing all the partial derivatives of s of u v up to including an order of d. So this is a partial derivative obtained of su comma v over d of over partial derivative of k plus l and partial derivative of k u of d l by v. By computing the derivative of the basis function, we get this below formula where u span minus p is less than equals to r less than equals to u span, and v span minus q is less than equals to s less than equals to v span. This is the diagram which represents the v spline curves V-spline derivative, surface derivative. Keeping in mind while applying the equation with respect to u, it yields the value of v, and while applying the equation with respect to v, it yields a value with u. So in generalization, the equation will look as follows. Next, we show the pseudocode of the algorithm. As you can see, the input is n, p, U, M, Q, V, P, U, V, D, and L, and the output is SKL, where SKL is the derivative of S of U, V with respect to U, K times and V, L times. For fixed K, 0, K, D, look, there is a local array temp which stores a vector product of NR, K, U, and TPRS while it is being multiplied with NS of Q, L, and V for L within 0 and D minus K. Array NU and NV are used to store the derivatives of the basis function. Now this is a visual representation of bicubic surface defined on u and v of these parameter values. The first and second partial derivatives are computed on u equals to 3 by 4 and v equals to 2 by 5. Then we show a derivative by manipulating the value of SUV equation. We formally differentiate S of UV with respect to U and with respect to V. So on the left hand side we get the derivative with respect to U, and the right hand side we get the derivative with respect to V. And following the generalization order, the value of the control point Pij is that of below. So by using the formulas as we derived earlier, we can come to corner derivatives. For example, at a corner u, v, 0, 0, we have the following equations. As you can see, s of u, 0, 0, s of v, 0, 0, and s of v, u, v, 0, 0 is as below. It is easy to note that the isocurves c of u0 and c of v0 over u gets these functions as based on the control points. That's all we have for surface derivatives, and then we'll talk a bit about design examples.
Hey everyone, this is Dhiren. I'm going to walk you through some design examples. So here's the first example. Here you can see the curves. With this curve we have modeled a cup in Blender, or it is called the chalice. And here we can see using curves we have designed a car model outlined and a face. So this is another example from Blender. This is a like curve to mesh technology. Moving on, we have the third example here. This is an example of curve surfacing modeling. Here we can see the different layers of the curves here that have been oriented together to make this beautiful model. The pot, you can watch it in this YouTube link. It's a really good video. And moving on, we have the GM lab where I show you the model. So this is the model we have created, a simple chess pawn using curves modeling. So I'll break it down into steps how we have created this, and we have done this in Blender tool. So I'll just go ahead and showcase you the curve which I designed. So this is the curve which I just highlighted. The next, so here we can see the curve that I have drawn. I'll just show you. I press tab and I can show you all the control points which I have used. So go ahead and press G. I can model it, I can control, like, keep it in different shapes and sizes and remodel this however I want. I can make a pot, a glass, anything. So these are all the control points you can use. I have just said before. So press tab again, so we get just the curve. And now I go ahead and make it into a model. So screw, and let me just change the axis to X, and voila, we have our beautiful little chess pawn. So that's it, guys. Thank you so much for watching. See you in the next one.